Hello, my name is Connor Harris, and my goal for this video is to tell you guys about neural networks and how you can build one from scratch. So this is a neural network. Alright, so a neural network is composed of weights. And the way in which we think about a neural network is to call each of these nodes a neuron. And a neuron is essentially a logistic regression model. So this neuron has values coming into it, and we're going to multiply those values from the previous layer. There are values going into the next layer, and we're going to multiply those values by weights and adding bias terms. So it's essentially linear regression, but then we take something called the activation function, something like this. This is a terrible sigmoid function. It looks something like that, where if you pass a negative value into the sigmoid function, then you get something very close to 0, and if you pass a positive value into the sigmoid function, then you get something very close to 1. And so you perform this activation function at every neuron, and what that does is that essentially normalizes the values passing through your network so that whenever large values enter that neuron, then the neuron is going to fire. And whenever small values enter that neuron, then it's going to go to 0, and so it's not going to fire. So that's why a neural network is called a neural network, because it's loosely based on the biology of your brain. Everyone's brain. Probably all of your brains. Okay, so this neural network has an input layer, a hidden layer, and an output layer. The architect of the neural network needs to design the network to specifically meet the needs of the problem in which you're trying to address. And so I want to give you an example of a problem, a very difficult problem, which a neural network can solve unbelievably well. Okay, these are handwritten digits. Imagine that you have a whole bunch of images, and each of the images contains exactly one handwritten digit. For you, I bet it's a really easy problem. I bet you guys are all over this. Like, you just look at this too, and you see this curve, and then the sharp curve, the sharp turn, and then this line right here, and your brain's, oh, that's a 2. And so what your brain is doing is it's identifying key features in the image, and then it essentially maps those features to a thing, and this thing is a 2. And the computer isn't very good at that at all, because imagine this one being overlaid over the other one, and none of the on pixels are going to correspond whatsoever. So this is a very hard problem. If you try to solve this with logistic regression, you're going to fail, because this is a nonlinear problem, so you need a nonlinear method. I'm not sure if I've said it already, but I did. These neurons are essentially logistic regression models. And when you combine all of these logistic regression models into a network, then what you get is a nonlinear model. And these networks, when trained properly, they can solve astonishing problems. And so as an engineer, if you ever encounter some sort of a problem, the opportunity may arise where you can make some prediction in your software, and you can amaze your user or build some incredible technology by applying this and making some predictions. So here's the math behind it. Okay, the problem that we're trying to solve is we're trying to identify handwritten digits. So what we're going to do is we're going to take all of the rows of the image, and it's a black and white image, and then we're going to stack those rows on top of each other so we get a vector. We're going to take this vector, and then we are going to pass it through the network. So this first input layer is just going to contain the pixels within the image. And then we're going to take that layer, and then we are going to multiply it by a weight matrix. This weight synapse here, we're calling this W1. And it also has a bias term B1, so that after you multiply the matrix and the pixel vector, then you're going to add this bias term. And the reason why is so that your decision boundary need not pass through the origin. If you didn't have that bias term, then your boundary will be forced to go through the origin, 0, 0, 0, 0, 0. So you do that. Oh no, that's not right. Okay. Now, after that, you take the sigmoid activation function so that you normalize all those values. And then after that, you multiply by W2, which is your second weight matrix. And then you also add B2, the bias term. And then after that, you take the softmax function of that vector, and the softmax will essentially produce a probability probability distribution for your output layer. This output layer, you need 10 neurons because we have 10 digits. And so the ith value in this vector will correspond to the probability that the digit in the image is equal to I. So if you add up all of these values, they will exactly equal 1 because that's a property of the softmax function. And so the question you're probably asking yourself now is, how do I find these weights? Because if you find perfect W1, B1, W2, B2, then you solve the problem and you can make whatever prediction you want. So here's how you do that with calculus. All right, the first thing that we're going to need to solve this problem is we need an error function. And I hope you can see that. So the error function is going to be a function which tells us how different our prediction is, that y hat is going to be equal to the prediction that our network makes minus what y, which is what it actually is. So for say that we have 0, we have the digit 0. The y vector is going to be 1 because the probability that that thing is 0 is 1. And then 0, 0, 0, 0 because the probability that it's a 9 is 0. So that's our y vector. Y hat is our prediction vector. And so we need some sort of a function that tells us how wrong we are. In the beginning, we're going to be horribly wrong because all of our weights are going to be totally random. So we need this function, and it has to be differentiable because if we can take the derivative of that function, that multivariable function, with respect to each of our weights, then we can take a step in the right direction for every weight. So we have W1, W2, B1, B2. So what we need to do is perform gradient descent, and what that is we'll take W1 and then we'll subtract the partial derivative of the error function with respect to W1. Because when we do that, the derivative of J, the error function, corresponds to the direction of steepest descent for whatever variable we're differentiating. And so here are those equations. Okay, so the partial derivative of our error function with respect to W1 is going to be the Jacobian of the softmax function. So you need the Jacobian matrix because the softmax function has all 10 of your neurons. There's no output layer. The output layer has 10 neurons. Then y hat minus y, that's going to be the difference in your prediction in your label, and then A1 transpose. So I'm not really going to go over these, but here are your functions. I'm just going to go ahead and say that for this problem, I ignored the Jacobian. I just ignored this, and I just did this, and that worked. Okay, so I made a mistake. These equations up here are the partial derivative of J with respect to W2 and the partial derivative of J with respect to B2. It's called back propagation because it's easier to find the partial derivative of J with respect to W2 because you're closer to the end. So you can see J depends on y hat depends on W2 and B2, and then it also depends on W1 and B1. So you can find these partial derivatives and then you perform gradient descent like this. So you update your weights like this. You have your weight is equal to your weight right now minus the rate of change of your weight, and that will take a step in the direction of steepest descent for that weight, so that your error will decrease over time. And so you do this as an iteration. You do this many times. You can do batch gradient descent or stochastic gradient descent. Batch is where you take your. Okay, I ran out of phone memory, but I was rambling anyway, so now I'm just going to go ahead and show you the results of all this math.